Assalamualaikum and hi, my name is Nadhir Rosli. So today I'm going to present about the topic is three-phase Y connected generator. So let's go. So firstly, as you can see, for the introduction is the star connection. So this is the primary imagination or primary sketching for the star connection. So as you can see, this is the inductor. So this is inductor. So what is star connection actually? In the star connection, the similarity ends either start or finish of the three windings are connected to a common point called star or neutral point. The three line conductors run from the remaining three free terminals called line conductors. So the wire are carried to the external circuit, giving three wire star connected system. However, sometimes a fourth wire is carried from 3 point to the external circuit called neutral wire. From the three-phase, 4 wire star connected system. Considering the above figure, the finished terminal A, B, and C of 3 windings are connected to form a star or neutral point. The 3 conductors named as R, Y, and B. That's mean red, yellow, and blue for 3 phase. Run from the remaining 3 free terminal as shown at the above figure. So the current flowing through each phase is called phase current, I phase. So as you can see, this is I phase, and the current flow through each line conductors is called line current. So this line current, I line. So what is the voltage across each phase is called phase voltage. So you can see this is phase voltage for this connection, and the voltage across 2 lines is line voltage. This is line voltage. Okay, next. What is the relationship between voltage in the star connection? Okay, this is star connection. As the system is balanced, so this is balanced system means that in all the 3 phases, example R, Y, and B, red, yellow, and blue, the equal amount of current flow equal its magnitude but displaced from one another by 120 degrees. Phasor diagram of connector is shown below. So as we can see, we need to see the phasor diagram. So this is the phasor diagram. The arrowhead of the EMF is EMF. Current indicate direction and not their actually the direction in any instance. Now E and R equals to E and Y equals to E and B equals to ERY in magnitude. There are 2 phase voltage between any 2 lines tracing the NYRN and RYN. So to find the vector sum of E and Y and negative E and R, E and Y and E and R, negative E and R, we have to reverse the vector E and R and add it any E and Y as shown in the phasor diagram above. Therefore, ERY equals to square root E square ny plus e square nr plus 2 e ny e nr cos 60 degree. So similarity EYB equals to ENB minus by ENY. Yes. EYB equals to ENB minus by ENY, or EL. Yes, or we can use the formula. Hence, in the star connection, line voltage is root 3 times of the phase voltage. Line voltage equals to 3 times phase voltage. Okay, what is the relationship between phase current and line current in the star connection? So, the same current flow through the phase winding as well as in the line conductors, as it is connected in series with a phase winding, where the phase current will be I and R equals to I and Y equals to I and B equals to IBH. Hence, in three-phase system of star connection, the line current is equal to the phase current. Remember, the line current is equal to phase current. So let's go to the objective of this project. So this project is to know about the different model connection in three-phase transformers, which is delta to delta, Y delta, YY, and delta Y, to learn about the relationship between winding voltage, line voltage, voltage phasor, and sum of three lines voltage in three-phase transformers. So that is the objective. So next is the methodology. So in this project, we need to evaluate the parameters of the electrical system in the context of the transmission, load of impedance, current, voltage acceptable, voltage drop based on BS 7671 or Malaysian Authority Standard. Also, we need to evaluate any analysis that active power absorbed by the load by using 3-watt meter method and 3 conventional measuring method. And we need to justify the normal operating condition of the electrical system and validate the study simulation. So this is the what we call chart or flow chart. So this is the methodology. First is project assigned by the lecturer. After project assigned by the lecturer, we need to draw a YY connection circuit using MPLAB. Draw it. After we draw, we need to calculate all the parameters. After we calculate all the parameters, we create a Y connection in the PC. So after we create the Y connection in the PC, we run the simulation to get the answer. It actually same with the calculation. So next, result and calculation. So calculate value. Rated generator line voltage is 33 kilowatt that I get. Line voltage is set 3. And voltage equals to line voltage divided by set 3 equals to 33 kilovolt divided by set 3 equals to 19.053 kilovolt. So for B phase, 19 kilovolt angle 0. So for B phase VBN 19.120. So for B phase VCN 19.053 kilovolt equal to 120. So Y equals 0, negative 120, 120, because this is in a positive cycle. In positive cycle, the degree will start with 0, after that negative, and then 120 positive. Okay, next is line current. In the star-star connection, the line current is same as phase current. IL equals to IP. Line current equals to phase voltage but divided by Z line plus Z load. So this is line current. Line current for IAA 19.05 kilovolt, angle 0, divided by 34 plus 23J plus 91 plus J9 equals to 147.63, angle 14.36. So for IAB 19.05 kilovolt, angle -120 divided by 24 plus 23J plus 91 plus 9J equals to 147 and 63, angle -134.64. So for ICC 19.05 kilovolt, angle 120 divided by 34 plus 23J plus 91 plus 9 equals to 147.3, angle 105.64 ampere. So next, what is transmission loss? Transmission loss is, we need to try and find VA 147.63, angle -14.36 ampere times by 34 plus 23J equals to 60.60 kilovolt, angle 19.28. So SN is the same, so I just keep it. So let's go to load voltage. So for the load voltage is VAM equals to 147.63, angle -14.36 ampere times 91 plus 9J equals to 13.50, angle -8.712 volt. So this is also same, this times by the J, so you can get a load voltage. So I just keep it because it's the same. So we go to the next. Power calculation. The real power equal to 3 times 147.63 times 13.50 cos -5.648 equals to 5.949 kilowatt. For the voltage drop, V drop equal to V supply minus by V load divided by V supply times 100 equals to 19.095 to 19.05 kilo minus 13.550 K divided 19.05 K times 100 equals to 29% that I get. So what is the, okay, this is the primary side for V phase. As you can see, this is the supply, the voltage, the ampere, the clock, the resistor and inductor, the transformers. So this is the diagram, and this is the graph. I get a stable graph that I get. So next is so for V line. V line, this is the graph. As you can see, the graph is that I get is very stable. This is the calculation that I get is daily with my calculation and my simulation. Okay, this is for I9. So this I9, this is for I9 simulation value. So as you can see, line current. This is also the graph. So next is for secondary side. This is for V phase. V phase, why the line is stable? Because V phase have a stable voltage. So the graph will be like this. This is the reading of the simulation. So next is for V line. V line for secondary. This is the graph, and this is the simulation. So 7953.47 for V4, 7894.4699 for V5, 7886.0078 for V6. So next is I line. So this I line for secondary, and this is their graph, and this is the simulation value. As you can see, So next, okay, for 2 watt meter, the graph is maybe this different a bit because we need to add on the watt meter watt meter things at least. So this is the watt meter. We put 2 watt meter to calculate between the what we call A and B lah. Okay, this is the reading. VAB equals to 3.64 K. VBC equal 23.521 K angle negative 120. VAC equals 22.559 K angle 120. VAN equals to 13.105 angle negative 30. VBN equal 13.21 K angle negative 150. VCN equal 13.31 K angle 90. So this is wattmeter and this is the okay, so the calculation VAN divided by Z equals to 13.105 K angle negative 30 divided by 91.J9 equals to 143.31 angle 35, 65 ampere. For IC, VCN divided by Z 13.310 K angle 90 divided by 91 plus 9J equals to 145.55 angle 64.35 ampere. The load power factor phase is 31.8. WA, what's WA? So to calculate the WA, we need to try VAB times IA cos 30 plus phase 23.64 K times 143.31 cos 61 equals to 1600.93 kilowatt. So this is also the same, so I just keep it on because we need to go further. So for total active power delivered to the load, WA, you need to add on WA plus WB because between the angle before WA, WB, if you need to find the total active power delivered to the load, we need to add on these two. So WA plus WB, we get total is 522.72 kilowatt. So if we minus it, WB minus WA equals to 1820 plus 8.83 832 kilowatts. For the time, set 3 WB minus WA time phase. For the time phase, set 3 WB minus WA divided by WB plus WA. So we can get 0.6279. So this is the graph that I get. So conventional method, VLL equal to 3V phase as we can see because of star connection. VP equals VLL divided by Z3 the 19.053 K. Since Z1, Z2, Z3 balance, I line or IN will be 0. So this is the for voltage time and conventional method. So we can see V1, I1, V2, I2, V3, I3. This is the simulation or calculation for conventional. This is the graph. Okay, this is the circuit diagram for conventional method before, and as you can see, just same like the first one because we just want to recheck what we do at 2 watt meter either correct or not. Okay, for discussion, later I check first. For discussion, as we can see, this project we just run the 3 phase. For the discussion will be the wire configuration, line current and phase current are same, but not for line voltage. and phase voltage, where in Y-Y connection, phase voltage is 0.577 times line voltage. Based on the data collected, the value between collected and measured on PCM value have slightly different for all parameters. In the context, current, voltage, power, and absorbed by loads, either using 2-watt meter method or conventional measuring method. For line voltage, actually value is 33 kilovolt, but from the simulation is 19.05 kilovolt, where it is 30 kilowatt different. Next, since line current and line voltage are same, students just measure the value of the line current, where the calculated value is 101.330 ampere, and the measured value where the calculated value has a very slightly different, and natural current is zero since the current load is 3 phase are same. So this is the discussion. For the conclusion that I can get from this project is why calculation is used to distribute power to everyday single phase applies found in house and office. Since the insulation is decided by phase voltage and connection between phase voltage and line voltage are equal, since the insulation level is decided by the phase voltage, and for Y connection, phase voltage is 0.55 times line, and hence insulation required in Y connection is nearly 29%, where it can be used for high voltage generation. That the insulation that will be required in the delta configuration for same line voltage, and cost for insulation will be reduced. In this experiment, the 3 connection generator in electrical system has been analyzed, and the parameters of Y-Y connection in the context of the transmission and load impedance, current voltage drop has been evaluated. Lastly, students also able to evaluate the power absorbed by using 2-watt meter method and conventional method measuring method. The experiment has been validated with simulation of Y-Y connection. That's all for today. If not enough, I'm so sorry, because I just tried my best for present this project. So thank you, sir, thank you, doctor, for this opportunity. Bye.